This is FE Peer Review. The date is September the 15th, 2021. Winter Hill to Isle of Man, observation looking past Blackpool Tower. I'll just pause here for a moment. You can read it if you like. Ranty put up this announcement a couple weeks back. It looks to me like he's planning a video where he's going to do some kind of observation. I gather from Winter Hill, looking across Blackpool Tower to the Isle of Man. He has been asking flat earthers, including Brandon, to provide him with their prediction of what he will see. And what we see in the image here is Ruhiv's prediction of what we will see. I thought it'd be fun to do a prediction of my own using one of my Sketchup models. Anyhow, the data. Ranty provided this data up in the corner here, a location and an elevation. I went into Google Earth. Bring up Google Earth here, and I marked the location of Winter Hill, the observation point, as well as Blackpool Tower and Snaefell, which is the highest peak on the Isle of Man. And I did paths between them, one path here and another path here, to get the distances between them. That was the basis for my data. I have compiled that data into this little image here. We have the elevation of 451 meters at Winter Hill, 158 meters for the top of Blackpool Tower, 621 meters for Snaefell, and the two distances of 105 and 41 kilometers in between. That's going to be the basis of the model which we will be looking at. I'll start with laying out some assumptions that are going on here, just to be very clear. The elevation and distance data is as presented before. I have not gone out of my way to fine-tune that data. I have not gone into detailed topographic maps to get exact elevations of Snaefell and so forth. Anybody can do that if they want to. There are times when it's necessary or helpful. In this case, we're working down to around the nearest meter or so, so I'm not worried about whether I'm half a meter off one way or the other. Second assumption, the radius of the Earth, I'm using an average radius of 6371 kilometers. Third assumption, curvature, drop calculations. Instead of doing them all myself from scratch, I am relying on Walter Bisslin's Earth Curve Calculator. And 4, atmospheric refraction is based on standard refraction per Bisslin. Now those are assumptions that are relevant to the models on a globe Earth. In addition, we have some assumptions related to the flat Earth model I will also be looking at. For the flat Earth model, the key thing is that perspective is based on a Euclidean idea of space. In other words, the horizon is at eye level. Lines below eye level remain below eye level until reaching the horizon. Lines above eye level remain above eye level until reaching the horizon. Lines above and below eye level do not cross each other. Actually straight lines appear straight, regardless of their orientation and distance in space. I found this charming little engraving off to the right here, showing various perspective constructions, drawn in perspective as well, which is kind of nice. And that is pretty much how perspective is taught in schools, how I learned it in school, and how I continue to use it professionally after going through getting my architecture degree and my engineering degree, and practicing in both those fields. It was never really necessary in the work I was doing, which involved buildings, to worry about spherical geometry when doing perspective work. It just didn't come into play. The largest project I worked on covered a site that measured 2 kilometers by 4 kilometers. But it was a whole collection of buildings. It was many dozen, well, actually hundreds of buildings if you want to count individual houses. But since they were all separate structures and not all connected to each other, it wasn't necessary to incorporate spherical geometry into the work we were doing, each building being standalone and the scale being what it was. None of that came into play. All right, let's move on to the Sketchup model here, and let's take a look at this little model I've got going. I enjoy working in SketchUp. It's a very convenient tool. It's not really designed for vast objects covering thousands, hundreds and thousands of kilometers, so it's a little bit crude for that purpose, but it gets the job done. What you see here is my SketchUp screen. I have 3 lines drawn side by side, and I'm going to look at 3 different models in a sense. The first one, which will be we'll call that the top line for now, that is the flat Earth model. What we have is a straight line which is actually straight, no curvature or anything like that going on. We have 3 objects. We have, where I'm circling the mouse, we have Winter Hill, and where I'm circling now is Blackpool Tower, and then at the end there, that's Snaefell. I'll zoom in a little bit. These are just simple geometric shapes intended to be easy to differentiate from each other when we look at the various perspective views, but they are in a sense to scale. For example, the distance from the peak to the base is 451 meters. That's the height of Winter Hill, from the peak of Winter Hill to mean sea level. The same for Blackpool Tower. We have the height is 158 meters. And then Snaefell, the height is 621 meters. The distances between them from Snaefell to Blackpool Tower, 105,000 meters or 105 kilometers. And then from Blackpool Tower to Winter Hill, 41,000 meters or 41 kilometers. Those figures remain the same for all 3 models. What changes is this straight line. In the second model, I have brought, let me see if I can get these side by side. Here we see the first model, the flat Earth model. Here we see the second model. This is R. This is radius of the Earth with no refraction considered. And what I've done is I've lowered Blackpool Tower below that straight line. You see the base of it is now below that straight line. And the distance below the straight line represents a drop of 132 meters. It is a drop of 132 meters, and that's based on the Earth Curve Calculator drop for the distance of 41 kilometers without any refraction considered. And then for the Snaefell, I've done the same using the appropriate amount of drop, which is 1,673 meters. Okay, so I have not drawn in the ground plane. But if I were to draw a curve that connected the base of this tower at the left, which represents Winter Hill, passes tangent to the underside of Blackpool Tower, and tangent to the underside of Snaefell, if I were to actually draw that surface, that would be our spheroidal Earth surface. The third version represents the same, but with atmospheric refraction, assuming standard refraction, which is equivalent to, we see it as an increase in the radius of the Earth. That's how it appears to us. And it's typically described as 7/6R. And I used, again, dimensions from Walter Bisland's calculator to get the drop, assuming standard refraction. The result of that being that the objects are a little less down from where they appear on the purely geometric view. See if I can get them both in the image here at the same time. On the left we see R, and on the right 7/6R. You can see that this one sticks up just a little bit more. That's also apparent when we look at the two Snaefell models. Okay, so that's how the model here is constructed. And I have made 3 viewpoints. What I have done is I have placed my camera exactly on the point of this Winter Hill and have oriented it so that we're looking straight over here at Snaefell. I will now go to the flat Earth view. We see Blackpool Tower well below the mountain, and if there was no intervening surfaces of any kind, we would see the base of the Isle of Man. Now we will go to the view on a spheroidal Earth without atmospheric refraction. We see now the top of Blackpool Tower at approximately the level of the top of the mountain, very nearly lined up. And now 7/6R. We see the top of the mountain appearing above the top of Blackpool Tower, and that's because with the further distance, the refraction is causing the more distant object to appear a little bit higher. So there you go. That's my prediction. Assuming standard atmospheric refraction, we should get something along the lines of what we see here, which puts the top of Blackpool Tower a little bit below top of Snaefell. Let's just take a moment and look at the SketchUp model a little bit more. For those of you who have not used SketchUp but who might be interested in trying it, there's a few nice little things here we can see. For a start, I have a display which indicates a horizon line. Now SketchUp, the workspace in SketchUp is an XYZ workspace, a Euclidean workspace. It is not a workspace based on spheroidal geometry. It does not include a globe Earth. The ground plane is a flat plane, and that is perfectly appropriate to the work that's typically done on SketchUp, which is things like buildings. So what we see here in this particular display, which we can change by the way, is a flat ground plane and a horizon line and a sky. And so this would be the Euclidean space I described earlier in the video. We're looking at the flat Earth version of what we would see, and I have used a tool, a convenient tool under camera called Position Camera, which allows me to put my viewpoint exactly on the tip of that block that I made to represent Winter Hill, so that I know that I'm located within the model exactly where I want to be based on the observation being done. The zoom feature. So Z is my keyboard shortcut for zoom. Now I just hit Z, and if we look in the bottom right hand corner, it says field of view 10 degrees. I can change that field of view just like I'm using the zoom lens on a camera. I am not physically moving forward into the model. I am just narrowing the field of view. So I'm going to change the field of view from 10 degrees to 3 degrees. If you note that in the bottom right hand corner it now says field of view 3, I'm going to hit enter. And that zooms us in much closer so that we can see closer the relationship between Blackpool Tower and the mountains beyond. I'm going to go ahead and update my scene here, update flat, and we'll come back to that. Now I'm going to go to R, my scene called R, my saved view, which was based on Earth radius with no refraction. I'm going to repeat what we just did. Z for zoom. I'm going to type 3 for my field of view. The figure in the box in the lower right has changed to 3. I'm going to hit enter. And you'll see as we move in closer, we're not physically moving in the model. We're zooming in as if we are just turning the zoom lens. And you'll see that the relationship between the peak of Blackpool Tower and the mountains behind does not change. We simply get closer to them. They simply get larger in our picture, but they are staying in the same relation to each other. So now you see how the top of Blackpool Tower and the top of the mountains pretty much line up. That would be the view we would have from Winter Hill if there was no atmospheric refraction. And we've zoomed in nicely so we can see it nice and clear. Now we'll go finally to the third view. We will zoom, set it to 3 degrees. We've zoomed in, and now we've got a better, we can see better that the Blackpool Tower is indeed lower, appears lower than the mountains beyond, because the mountains, being further away, are more affected by atmospheric refraction and have been raised up visually more. I'm going to update that. And we can see them side by side, with refraction, without refraction, and flat. And in the flat Euclidean workspace of SketchUp, I've left the default horizon view on so that we can see that it crosses the mountains at precisely our elevation of 451 feet, of meters, 451 meters. The mountains rise up a little more than where we are. We are below the top of the mountains. Okay, that pretty well sums it up. We have my prediction. I will go back to that. My prediction for what's going to be seen in the view from Winter Hill over Blackpool to Isle of Man. I hope you enjoyed this little video. I recommend Ranty Flerfspective's channel. I believe he's the one that's going to be publishing the view, and he is the one who did request predictions, so you now have mine. If you like this, click the like button. Remember to leave comments, and I'll talk with you again soon. Bye-bye.